The flood in Nepal may be only the beginning. On August 26th, a catastrophic chain of events began in the Himalayas near the Nepal-China border. A glacier collapsed, a huge mass of ice and rock rushed down the mountain, a river system was overwhelmed, and the resulting debris flow and flood traveled nearly 100 kilometers downstream. Hundreds of people have died, and more than 1,000 remain missing. But now a new danger has emerged. A barrier lake formed upstream. The lake has already begun overflowing, and authorities are warning that the risk of another destructive flood has not disappeared. So, what actually happened in Nepal, and why is the disaster still evolving? Let's start at the beginning. On August 26th, a large section of the Langtang-Lirung Glacier, together with the bedrock beneath it, collapsed from the northern side of the mountain. Langtang-Lirung rises to more than 7,000 meters above sea level in one of the most rugged environments on Earth. When the glacier and rock mass collapsed, it didn't simply fall onto the valley floor. It accelerated downslope, carrying ice, rock, water, and huge amounts of loose debris with it. As the mass moved downward, it picked up even more material and water from the mountain environment. This transformed the collapse into a rapidly moving debris flow, and once that material entered the river system, the disaster became a flood. So, how far did this flood travel? Nearly 100 kilometers. The debris flow and flood moved through the Bhote Koshi and Trishuli river systems, affecting communities and infrastructure far downstream. The flow was powerful enough to bury or destroy roads, bridges, buildings, and other critical infrastructure. And in one part of the Trishuli river system, the water level rose by around 9 meters in just 30 minutes. That's an extraordinary rise over an extremely short period of time. But then, another question appeared: was this actually an earthquake? At first, the seismic signal made the event look like one, but scientists now have a different explanation. Seismic analysis detected energy equivalent to approximately a magnitude 5.2 earthquake, but that does not mean a magnitude 5.2 earthquake caused the glacier collapse. Instead, the seismic waves were generated by the enormous mass movement itself. In other words, the mountain moved so violently that it produced seismic energy comparable to a magnitude 5.2 earthquake. And about 3 hours later, another seismic event was detected with energy equivalent to approximately magnitude 4.2. So the earthquake was not necessarily the trigger. The collapse itself generated the seismic signal. But this raises another major question. Was climate change responsible? This is where the science becomes more complicated. Scientists cannot currently say that climate change directly caused this specific collapse. There is no evidence allowing us to simply say climate change caused the disaster. But that does not mean climate change is irrelevant. The Himalayas are warming, and warming can change the conditions that hold high mountain slopes together. Glaciers are losing ice, snow conditions are changing, and permafrost can degrade as temperatures rise. Permafrost is ground that remains frozen for at least 2 consecutive years. When ice within frozen ground weakens or disappears, some steep mountain slopes can become less stable. That can increase the background risk of rockfalls, landslides, ice avalanches, and other high mountain hazards. So the scientifically accurate answer is, climate change has not been confirmed as the direct trigger of this event. But a warming mountain environment can increase the conditions that make some of these hazards more likely. That distinction is extremely important. And now we reach the most important part of this story. Is the danger over? No, because the first disaster created another hazard. The enormous amount of ice and rock that entered the river system created blockages and unstable debris dams, and near the Nepal-China border, a major barrier lake formed near the confluence of the Chochen Kola and Purpo Tempo rivers. Think of it as a temporary natural dam. Instead of flowing normally downstream, water becomes trapped behind a wall of rock and debris, and the longer that lake holds water, the greater the potential volume that could be released if the barrier fails. So how much water are we talking about? Chinese water authorities initially estimated that the lake contained around 1.5 to 2 million cubic meters of water. Then they warned that approximately 3 million more cubic meters could flow into the lake over the following 3 days. That's roughly equivalent to 1,200 Olympic-sized swimming pools of additional water. And this is where the situation became even more serious. Rainfall was continuing in the region. More rainfall means more water can enter the river system, and more water entering the lake can increase pressure on the natural barrier. So, what happens if the barrier breaks? The lake could suddenly release a large volume of water downstream. This type of event is known as a lake outburst flood. And because the water would be released from a naturally dammed lake, the flood could intensify extremely quickly. It could carry sediment, rocks, trees, and other debris downstream. That means the danger is not simply more water. It could become another debris-laden flood wave. And there is an important update. Authorities did not simply wait for the lake to become more dangerous. Chinese authorities deployed engineers and specialists to the area. They used aerial surveys, remote sensing, and terrain modeling to assess the lake and the stability of the surrounding area. One option being investigated was creating a controlled drainage channel, allowing water to escape more safely instead of waiting for an uncontrolled breach. But then, the situation changed again. On August 28th, Chinese authorities reported that the barrier lake had begun overflowing. The increasing water and unstable terrain forced rescue operations in the area to be temporarily halted. Authorities were also warning about the possibility of further flooding, landslides, and other secondary hazards. So the situation is no longer simply, will the lake fill? The lake is already overflowing. Now the question is, how much water will enter the system? How stable is the natural barrier, and what happens downstream? And this is what makes the Nepal disaster so dangerous. It is not one single hazard, it is a cascade. First, a glacier and underlying rock collapsed. Then ice and rock accelerated down the mountain. The debris entered the river system. The river became a channel for a massive debris flow and flood. The flood traveled nearly 100 kilometers downstream, and now the same disaster has created new unstable water bodies and debris barriers. One hazard created another and another. So is another catastrophic flood guaranteed? No, scientists and authorities cannot say that another massive flood will definitely happen, but the potential for another sudden flood remains a serious hazard. And that's why authorities are continuing to monitor the lake, the surrounding slopes, rainfall, and downstream rivers. The tragedy in Nepal is therefore much more than a story about a flood. It is a story about how interconnected the Himalayan environment is. A glacier can collapse, a mountain can move, a river can transform into a debris flow pathway, and a temporary natural dam can create a new lake which can become the source of another flood. The first flood has already happened, but the disaster is still evolving. The lake has begun overflowing. The mountains remain unstable, and authorities are still watching the water, because in the Himalayas, the danger doesn't always end when the first wave passes.